Okay, hello CCTI pre-calc classes, Mr. Pashar here. I'm going to do one more video for you on half-life problems. As you have seen from your textbook, you have a few exercises on half-life. And when we think of half-life, we think about a radioactive substance and how it breaks down. It breaks down essentially over time gradually, and we call this time its half-life. So half-life meaning how long does it take for half of the substance to break down? A half, a half, a half, a half. So we may have maybe 40 milligrams of some substance, and how long does it take for half of it to go away? From 40 to 20, we could determine that using a model, a mathematical model. So in our last video, we looked at how we were given an abstract model, and then we rewrote the model in terms of the data. And that's what we're going to do here. We're going to be given an abstract model, a decay model, and what we're going to do is pretty much morph that model into one that's workable for the given conditions. So the problem I want to direct your attention to is a very good problem. It actually comes in the chapter review section on page 390, and we're going to look at number 23. So when you deal with half-life problems, typically there's two steps. The first step is to find K, and we'll talk about what that means. And the second step is to find T. So T stands for time stamp. K is some kind of constant of proportionality. In other words, K is kind of this number that keeps the model balanced, if you will. It helps us to get to where we need to be in our new model. So let me read 23 for you, and again, read along in your textbook. This is on page 390. If 40 milligrams of strontium-90 radioactively decays to 12 milligrams in 30 years, find its half-life. Use the formula A equals P times E raised to the minus KT power, where P is the initial amount and A is the final amount. We want to round our answer to the nearest tenth. Okay. So here's what has to be done. We're going to do just like as it says. We're going to find K first, and then the second step is we'll use K to find T. So you need K to get the T and not vice versa. So this is the model that we're given. The model we're given is A equals P times E to the minus KT power. And that should make sense because this is a decay problem, right? Radioactive decay. So it needs to be minus for that K. So step one is we're going to find K. And again, this is where all your skills come into play with solving those logarithmic equations and exponential equations. That's why even before that, we had to learn how do we go ahead and simplify logs and exponentials using those rules. So you're really behind the eight ball if you can't go back and do those things. That's why it's so important. That's why I try to condition you before we had to leave school on to how to do those types of things. So find K. So here's what our equation is going to look like. 12 equals 40 e to the minus 30k. Now you're wondering, where do these things come from? Well, the 12, this is what it's going to decay to 12 milligrams, right? We were given in terms of milligrams. So it's going to decay to 12 milligrams, and 30 stands for the time stamp in years. So 30, that's what we're looking at. So we're just filling in the information that we're kind of given. Remember, here's your formula. A equals P. P stands for your initial amount. This is what the amount reduced to. T is the time stamp, okay? So we're going to go ahead and solve this thing for K. So first step I would do is divide both sides by 40. So you're going to get 12 over 40 equals e to the minus 30k, like that. So we could go ahead and reduce that. That takes us down to 3/10 equals e to the minus 30k. And now you have a base E equation. So that means we're going to take the ln of both sides. So we got the ln of 3/10 equals the ln of e to the minus 30k. Just like that. You have the ln of 3/10 equals negative 30k. Remember the ln and e are wiped out, they're gone. So just to save us some time here, when we do this, we'll divide both sides by negative 30. And that implies k is this number here, 0.04013242268. Remember the importance of writing out all those decimals. Remember when we were still in physical class, we don't want rounding errors, so we want to be able to take this decimal all the way to the end. So that's what k is when we solve. K is the value 0.04013242268. And it's pivotal because we need this to go forward. So that's your k value. So now what we're going to do is go back to the model and use this k value that we found here. So we go back to this initial formula, A equals P times E to the minus KT. And we're just going to go fill in what we have now. So the A is going to be 20 in this case because this is the amount of substance. The half of the 40 milligrams is 20. 40 stands for the initial amount of the substance times E, and it's going to be raised up to the minus 0. It's this decimal expansion right here that we have. Negative 0.04013242268 times t. Remember, t is the time. That's what we're trying to figure out. Remember, step 2 says find t. So we found k. Going back to that same model we were given to start. 20, that's the half of the substance. It's half, right? Half of 40 is 20. 40 is the initial amount of substance times E raised up to the k times t. And we're going to go ahead and solve this thing for t. So that means we'll divide both sides by 40. 20 over 40 is 1/2. So we got 1/2 equals negative e to the negative, I'm going to call it mass times t because I'm too lazy and I don't want to write out all those decimals. But we'll take the ln of both sides. So ln of e to the negative mass times t. Now that mass, that decimal now is going to come down here. So I will write it out this time. It's going to be negative 0.04013242268t, written that way. And then we'll divide both sides by that ugly decimal, right? And when you do that, you're going to get a positive number. That should make sense because you're dividing by a negative number, okay? But the ln of 1/2, that also represents a negative number. So therefore, t, negative divided by negative, is going to be positive. So when you do this and you round, it's going to be about 17.3. So in terms of this problem, they ask you, what is the half-life? That is t. So the half-life is about 17.3 years. That's your final answer. I know it's kind of confusing. It's a lot involved in one problem, but once you do a few of these, then you understand the process. So again, first step was to find k. So we found k. Then we plug back into the original model to find t because t is the half-life. So for half of this substance to reduce, so to go from 40 milligrams of this substance down to 20 milligrams of this substance, it takes 17.3 years. And then to go from 20 down to another half, so down to 10, that would take another 17.3 years. And then half of 10 would take another 17.3 years, and another half would be another 17.3 years. So it does take a considerable amount of time for radioactive elements to break down. So with that being said, I hope this additional example will help you with your exercises. Again, if you have any other specific questions, feel free to email or call. And I hope this video finds everybody healthy, well, and sane. And I'm hoping I'll be able to eventually see all you guys in the near future. I'm kind of betting all of us will be happy to be back in class sooner than later. So until next time, and until then, I'll see you when I see you.